I'm going to start last couple of lectures in the representation theory course. Well done for surviving to the end of term. Woohoo! We've seen character theory, we've seen lots of multilinear algebra stuff, constructions of new representations from old. And then last week was induction, a couple of weeks, which was technical but important. Not going to use induction today, but we are going to see a couple of applications of character theory. Well, one application really, that's this famous theorem. I'm going to state the statement later. I'm going to first use character theory to prove a nice arithmetic property of the character table, namely that the degrees of the reducible representations all divide the size of the group. Strange fact. Useful if you're completing character tables. So it further narrows down the work of finding some missing character degrees. You know, maybe you're missing 3 character degrees or something, and the sum of their squares is known. Also, they must divide the order of the group, so in particular they're quite small, right? Irreducible representations must have degree most the square root of the size of the group. Let me just scratch that. Let's just get on with it. So, to prove these theorems, I need, I'm afraid, a little something from algebraic integers, algebraic number theory. So hopefully many of you will continue to do algebra with a bit of number theory thrown into the mix. In particular, so I won't advertise algebraic number theory next term. Where you will see algebraic integers and a lot more. But also, if you like this course and you want to do more representation theory, then please don't miss the course called Lie Algebras, again being taught next term. This is less obvious than this one as a continuation, because why Lie Algebras, no one knows what they are until you come to the course and you do it, and you discover that if you like linear algebras, you must do, because you've survived this far in representation theory, then it's the thing for you. Right. Advertising over. So, what are algebraic integers? What are we talking about? First of all, everyone knows what algebraic numbers are. What's an algebraic number? It's a complex number which is a root of a polynomial equation with rational coefficients. I think you've seen this idea before. Definition. It's a zero, or a polynomial equation with rational coefficients, or if you like, that's the same as saying that the subfield generated by z over q is finite, etc., etc. So this is an important idea studied in algebraic number theory, for example, root 2 and root 5 and such. I'm concerned here with integers. The definition is a little bit counterintuitive, well, it's a bit strange. So an algebraic integer same condition holds, but the leading term can be chosen to be 1. And all the coefficients are, of course, integers. Okay, there exists alpha n minus 1, alpha 0 in z. I'm not going to write down alpha n. Oh, I've got it wrong, haven't I? This, as stated, includes pi, right? It could all be 0. Right? Not all 0. I mean, this one's all right. They could all be 0 and n and z is 0. That's fine. The other comment here is that if they're not all 0, then you can just sort of clear denominators in this equation. You might as well assume that the alphas are integers. Right? So it could be like, I don't know, 2z plus 3. That's an algebraic equation. Z equals minus 3 halves. It's a rational number. That's okay. But this guy is not an algebraic integer. Okay. Any questions in the definition? No? So, a set of such things is usually called Q bar. Okay. And a set of such things is called A. Good. Examples. Well, obviously, every integer is an algebraic integer, because every integer n is a solution of the modic polynomial equation x minus n equals 0. Roots of unity, right? So e to the n is 1. Some positive integer n, then of course zeta is a solution of a monic polynomial equation t to n minus 1 is 0, therefore roots of unity are algebraic integers. Clearing denominators works. So in a formula, I can say that if we allow ourselves to multiply every algebraic integer by a rational number, we will get all algebraic numbers. Certainly A is contained in Q, right? Being an algebraic integer is a stronger condition than being an algebraic number. This is a Q vector space, so this inclusion is clear. Yes? And the reverse inclusion is clearing denominators. Yeah? Shall I do this? For this inclusion, say, I have a algebraic number called Z. With alpha I in Q, not all 0. And then if I multiply this through by m to the n, pick m, some gigantic positive number, and multiply through by m to the n, and maybe even m to the n plus 1, why not? Argue with that, but the point is that m is variable, and I can absorb m to the n to the z, right? And that still keeps me an m for the alphas to kill any denominators in alpha. mz to the n plus m squared alpha n minus 1 mz to the n minus 1 and so on. So on. So this is what clearing denominators means, plus m to the n alpha 1 mz plus m to the n plus 1 alpha naught 1 0. Good. And obviously then m can be chosen to ensure that m times each alpha I is an integer. Right. I screwed up. Okay, so I don't want to spend long with this. It's true. All the coefficients are in Z, and the first one goes M alpha 1. Is 1. Then, finally, this is not so important, right? So this proves that then mz is an algebraic integer, which proves the reverse direction. But the direction of the statement I really want is to understand algebraic integers which have to be rational numbers. So this should be the old notion. I need this for the rest of the lecture. So again, this is true, obviously. And the other direction, let's do this properly. Let z be a rational number. It's also an algebraic integer. And assume that R and S are co-prime. Write down a modic polynomial equation with integer coefficient satisfied by z. And then plug in z is R over s and multiply by s to the n. What do we get? We get s, no, we get r to the n plus s alpha n minus 1 r to the n minus 1 plus o dot plus s to the n minus 1 alpha 1 r plus s to the n alpha naught is 0. And here, of course, with all alpha I integers. So this is now an equation in integers. Everything inside is an integer. But in particular, we'll get that r to the n is a multiple of s, and that's not good because r and s are co-prime. So the only way this is possible is this S1, S is 1. Good. So, the only algebraic integers which are rational numbers are actually honest integers. So in this sense, this definition does, in a slightly convoluted way, generalize the notion of integers. There is also an algebra geometric way of thinking about algebraic integers, if you are so inclined, off the syllabus definitely, some kind of integral closure of integers. So if you think of integers as a curve, then the algebraic integers form some kind of normalization of that curve in the algebraic numbers. But if that means nothing, just So, seen some examples of algebraic integers. Namely, roots of unity. Roots of unity appeared a lot in representation theory. So next I'm going to prove the following theorem. A is a subring of C. I need this theorem for the group theoretic implications. So to prove this uses the following proposition, which is actually turns out to be an equivalent condition on a complex number to be an algebraic integer, and it's a module theoretic condition. So, this proposition says that algebraic integers are precisely those complex numbers which normalize a finitely generated abelian subgroup of C. More precisely, suppose I have such a thing called M is a finitely generated additive subgroup of complex numbers, and suppose Z, the complex number, normalizes this lattice, this subgroup, in this sense. Multiplication by by Z keeps you within M. Then, in fact, Z must be an algebraic integer. Proof is rabbit out of the hat. Okay, where do we get this monic integer value, integer coefficient polynomial from? So it's going to be a characteristic polynomial, a matrix. This is a very important proposition. Let's do it. So write M in this way, which we can. It doesn't matter that the BIs are a basis for M as a Z module, although if you are completely on top of your rings and modules material, and I'm sure all of you are, then you will remember that a finitely generated torsion-free module is free, so you might as well choose a basis, but it doesn't matter. Well, I've got this condition that Z normalizes these things, so I can write down the product Z times Vj as an integer linear combination of the V's. For each j, I can choose d integers u1j, u2j, unj, such that this formula holds true. And now we'll forget about numbers and just do a bit of linear algebra. And so, if you now think about what this matrix is doing, just to consider this matrix. It's a d by d matrix with entries in Z. And let G be its characteristic polynomial. The U so the characteristic polynomial of a matrix of integer coefficients has integer coefficients, and furthermore it's monic. Okay. A monic polynomial. Good. Now, let's think about what this is saying. whose entries are the bi's. And then this equation is saying exactly that u times this vector is z times this vector. So hence, V is an eigenvector can't be 0 because when m is 0, then z is 0. V is an eigenvector of u, and so by linear algebra, with eigenvalue z, of course, and so indeed, the char quality of u vanishes on z, and that gives us the required harmonic equation with integer coefficients satisfied by z. Okay? Very important proposition. Remark, converse is also true. That is to say, if you have an algebraic integer z, then there exists at least one m with this property. You just take m to be the subring of the complexes generated by z. You can check that this satisfies the condition. Good. So now let's do the theorem. So what's not obvious? What's this subring anyway? It's something close under addition, subtraction, multiplication, and contains 0. 0 is okay. Contains 1 as well. 1 is okay. They're both integers. So all you have to prove is that it's closed under addition and multiplication. I have two algebraic integers. Then their sum is an algebraic integer, and their product is an algebraic integer as well. So none of these things are obvious. Right? Fun exercise is to check this directly. Take root 2 and cube root of 3 or something. Which harmonic integer polynomial equation does this sum satisfy? You can find it. Not obvious what it is. Fortunately, this bit of magic comes to the rescue. So all we have to do is exhibit an m. And so we just take m to be the subring generated by alpha and beta. And you observe that it's finally generated as an abelian group. So if alpha satisfies a monic equation of degree n, and beta satisfies a monic equation of degree m, A's and B's integers, then you can check that this set, the set of integer linear combinations of monomials and alpha and beta, where the exponent is less than the pair nm. So the claim is that this set is closed under multiplication by alpha and beta. And therefore it's a subring. Therefore it's equal to n. And why is it closed under multiplication by alpha and beta? Because if you multiply such a thing by alpha, the worst that can happen is that the I overflows. I might have been alpha to be I might have been n minus 1, but if you get alpha to be n, then you can rewrite it using this equation we did it for beta. Okay, so this is actually automatically a subring. And it's visibly finely generated, over Z because this set of such pairs is finite. And being a subring, right? This is a subring already. C and M is finely generated over Z, and M contains alpha and beta. We deduce that M contains alpha plus beta and alpha beta, and therefore it normalizes them. So you can apply 7.4 to get alpha plus beta and alpha beta both algebraic integers. Any questions? Good. So that's all I'm going to say about algebraic number theory. It's an important fact that algebraic integers form a ring. Now let's go back to group theory. I want to prove the following corollary. Goal, we're going to prove corollary 7.8, which says that if G is a finite group and V is an irreducible C-linear G representation, also known as a simple CG module, then the degree of this representation, namely the dimension of the underlying vector space, is a factor of the size of the group. That's going to be our first application. To do this, we're going to do some messing around with conjugacy class sums and algebraic integers. Okay, so the idea of this proof is to look at the value of the central character of V at the conjugacy class sum of some element. That's one idea. The second idea, I think, is to use row orthogonality. Shall we work backwards and see how this works?
What's the central character?
I did it in week 3.
Really?
Maybe. There was something called Shor's lemma. Shor's lemma said that in our situations, if we have a finite dimensional module over some algebra over an algebraic closed field, then central elements, well, then the endomorphism ring of that module is a copy of the ground field, no interesting endomorphisms, but central elements always act by endomorphisms, therefore they must act by a character, by a scalar, and the value of that scalar is the central character of. So the central character is the function from the center of the ring to the scalars, which encodes how the center acts on the module. Let me go that down. B is a simple and finite dimensional A module for some C algebra, just to keep things simple. A, then the central character, B is the function. Now I have to be careful because I can't call it chi, which is a right pain. I'm not going to give it any names. Right? It's a function from the center of the ground field, which sends z to the scalar zb such that z dot b is scalar zbb for all vb. Right? This scalar exists by Shor's lemma. Shor's lemma underpins all of this. I used this idea to prove that the number of irreducible representations is not too big. Okay, so let's see if we can prove, start off the proof of this corollary, the goal. I want to show this divisibility. I'm going to use row orthogonality plus values. So let's start with row orthogonality. I've got an irreducible representation, so the inner product of the character of V with itself is 1. Right? Row orthogonality is this number. Right? Because V is simple. And what does this say? Let's rewrite this. That's 1 over mod G. And we break things up into conjugacy classes. Let's say that there are R conjugacy classes with representatives G1 up to GR, and we have to weight the sum by the conjugacy classes, and then we'll have to do mod chi is fixed of gi squared, right? That's the inner product, okay? Now I'm going to break up this norm squared and multiply by mod g. I'm going to say that for a complex number u, mod u squared is u bar times u. Ready? Okay. I'll massage with sum like this, as you do. Okay. What does this have to do with dim V? It's not clear, right? So you keep on massaging. Multiplied through by mod G over dim V. That's the number that we want, right? That's a rational number, a priori. We want to show this is an integer. So it will suffice to show that this is an algebraic integer. Okay? So if we multiply it by that, we will get there is a lemma I think this one's called 521a. It tells us that the character value of the inverse of a group element is the complex conjugate of the character value of a group element because you can diagonalize a group element in the action, right? And the eigenvalues of the inverse are the complex conjugates of eigenvalues. So when we do this massaging, mod g goes away to be replaced by some other horrible thing, namely the degree. Okay, great. So, good. So, there's going to be a lemma, 2. Lemma 7.5. Says that chi v of g I inverse is an algebraic number, and the proof is so trivial I'm not going to write it out. Right? If you've been following, I've done it already. And because the character values, the sum of eigenvalues, the eigenvalues are all roots of unity algebraic integers, sums of roots of unity algebraic integers by theorem 7.3. Okay? So this one's all right. What about this one? What a mess. This keeps things interesting, doesn't it? So, theorem 7.7a tells me that this thing is also an algebraic integer. Okay, we're going to prove this. So what is this thing? Well, this is a sum of roots of integers, so that's an algebraic integer. That's a positive integer. That's a positive integer, so this is a, it's all right. It's an algebraic number. But the claim is actually it's an algebraic integer. So if you believe this for a second, then the proof's complete, because the left-hand side is a ring theoretical expression of algebraic integers, therefore an integer. And therefore the right-hand side is also an algebraic integer, and then that example which I did correctly told us we're done. Right, so hence, in this equation, left-hand side is an algebraic integer by 7.3, and so the right-hand side, which is the rational number we want, it's in A, and a rational number, and that's by 7.2 by example. And that's exactly what I want. I want to show that this fraction is a whole number, which means that the didn't be divides. Any questions about the proof of 7.8? So that motivates looking at this thing. So that's where the other idea comes from. So it turns out that this is exactly the value of the central character of V on the conjugacy class sum of GI. And it may not be clear why that that's enough. That's the last step. So I'm going to prove now 7.7a. Which says that B is simple and G, then the conjugacy class sum of G, which is the central element, acts on anything in V exactly by this number. So why is that? It's actually quite easy. It's just Shaw's lemma, right? So the existence of central character means that this action is indeed given by a scalar, but we can tease out the scalar by taking traces. Did I screw up? It should be dim B. And that's where the dim B comes from. So we know that by Shaw's lemma, the central element, that is this conjugacy class, acts on V by an endomorphism of CG modules, which is reduced to C by some scalar. Scalar. Lambda. Just get bogged down with by notation and partial notation. So, some x in the conjugacy class, x, right, that's a group element, group ring element, sorry, acts on every vector just by multiplying by take traces. We get the trace of the action of so rho B, of course, is the representation afforded by the CG module V. Right? Is equal to what? The trace of the scalar endomorphism lambda. That's lambda times dim B, isn't it? The matrix of a scalar is lambda, 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 dim B times. Good? Characters are traces of the group action, right? So this is exactly a character values, which is where we started. That's that number. And so, as I promised, we can tease out lambda from this equation because characters are constant on conjugacy classes. So it's going to be this thing repeated mod GG times, and the character value G divided by dim B. That's what I collect. Any questions? Take traces in the action and say, look, easy. But why does that help? I don't care that this thing has a nice representation theoretic meaning, right? It's the value of a central character. I want it to be an algebraic integer. Why isn't it an algebraic integer? The reason is that conjugacy class sums multiply very nicely inside the complex group ring. form some kind of very nice commutative, lightly generated subring of CG. And therefore its image, under the representation, forms a finely generated division subgroup of C, stabilized by the action of any particular conjugacy class sum. I better write this out. That's the proof in words. So, now comes, we will now show that this thing is an algebraic integer, but first the lemma. It says, if I have the conjugacy class says of the group G listed, all of them, and then I'll go ahead and consider their class sums, and that form the set of integer linear combinations of the class sums. I'll call that S. So what's that explicitly? It's what I said, but in formulas. Consider this set additive subgroup of CG. Whoops. Makes sense. Makes sense now, right? This is a subset of CG. And the statement is that this is closed under multiplication. Oh no, I've destroyed the universe.
Spray that.
What's that?
Like a spray bottle.
Spray! Thank you. See if that helps. Yes. Very good. Just a black pen which is dirty. Red one's fine. Okay. So the statement is that S is a subring of CG. Subring of CG, I want to write that's, but actually, obviously, all these things are central, right? So it's even a subring of the center. We know what the center of the group ring looks like, right? It's C to the power S, because these conjugacy class sums form a basis of C basis. I think the claim is that actually they multiply correctly. Why is that? We just do it. Just compute how conjugacy class sums multiply. So you fix indices I and J and consider the product of two class sums. It's supposed to expand out. This is the sum of all things in the first conjugacy class. This is the sum of all the things in the second conjugacy class. And you multiply them all out. It's not clear what you're going to get, is it? But whatever it is, it's a grouping element, whatever it is. And so I'm going to break up the group into union of conjugacy classes, C1 up to CS with dummy variable K, right? And so any element can be written like this, with some scalars a of z, depending on k, of course. Okay, but obviously I and j are fixed, so better. So in I, j, and k. Okay, Z, and that's a complex number. But it's better than that, right? It's actually quite coefficient and see how many times does Z appear as an x times y? So now we'll fix Z. I suppose, fix k and z. How many times does x times y equal z? Well, I don't know. I'll write down a formula for it. Right. So good. And now the observation is that this set is equivariant with respect to conjugation action. You conjugate things, you get the same set. If I call this set, I and j are fixed, right? So if I call this set, I don't know, t of z, and the claim is that all g in g, some other variable, the function which sends pair xy to the pair conjugate by g is a bijection from t of z to t of of z. Right, so here, u to the g means g inverse ug. That conjugate. X times y equals z, therefore x, y conjugate by g. It's conjugate by g, but conjugation by g is a group automorphism. Therefore x to the g, y to the g, z to the g. Right? So the function is well defined. And furthermore, right, if you conjugate x, x is an element of Ci. If you conjugate it by G, you're still in Ci because Ci is a conjugacy class. So we'll have a well-defined function. I don't know, called conjugate by G. And obviously, if I apply TG to G inverse of course Z, the G is its inverse. Okay, I am overkilling this claim. At some point it will become obvious. So therefore, that's great news. Hence, A, I, J, K, or Z does not depend on Z, only on the conjugacy class. That's it. So these structure constants, A, I, J, K, you can, if you know the K table of groups, you get some interesting commutative ring. Ci hat, Cj hat, sum of K, A, I, J, K, that's the common value independent of Z, right? Ck hat. And that's being an integer, that's the other thing. Why? Because it's the size of a set. Is immense. And that's what I wanted to prove in the lemma. So that being done, the corollary of the theorem 7.7b says, with the notation of 7.7a obviously, as the numbering suggests, the values of a central character of a conjugacy class sum is always an algebraic integer. V still has to be simple, otherwise the Schroeder lemma thing doesn't work. Right, so V simple, G random, little g random, I mean, claim this, but you will get integer, y. Well, you look at the action of the group ring, then row tilde, I think, may have appeared somewhere on the sheets. The C algebra homomorphism induced by row. Just linearize the group homomorphism. Whatever it is, it's a ring homomorphism, and by Shor's lemma, right, the restriction of this guy to the center is the central character, if you like. Right. That being the case, row tilde sends the center into scalars, Shor's lemma, right? And therefore, row tilde of S is also a subring of C. And the image of a ring homomorphism. But S is a finite geometry being group. This is a valid M. S is by definition the Z-span conscious class sums. If I apply a ring homomorphism to this doesn't change. Finite generating Z module. And what? Well, row tilde of G to the G hat preserves it. Right? And so by proposition 7.4, this thing is an algebraic integer. But we saw what this is. Good. So that completes proof of 7.8. Late. Right, let's take a 5-minute break, and then we'll do some more stuff. You first clear the view of those. You can do that in a way that the ideal generated by all the coefficients throughout. You take the LCM and then take the first coefficient and divide by it. So you have a preliminary equation, all coefficient integers, and the GCD at the bottom. First coefficient for alpha m still. So let m be LCM divided by. So all because when you do that, sorry, to clear the boards. You've got more questions? Yeah, not now, I'm sorry. Let's talk after the lecture.
So are you lecturing any other courses next time? Are you lecturing any other courses next time?
I've done my fair share.
I don't see it.
In good hands with Lucy. He's doing the algebras, I think. Victor Flynn is doing algebraic number theory as far as if I remember correctly. Is that right, or is it Big Green?
why is it three?
Okay, let's resume. So now we're going to prove the following theorem, which was one of the first major applications of character theory to pure finite group theory. So this was proved by Burnside somewhere around then, 1904, at the time when finite simple groups were interesting and people didn't really understand them. I had some examples, and people were interested in classifying them, I think, at the time. And so at this point you had Silo's theorems done by Silo in 1870 or something, which imply, well, not imply anymore, they tell you that P groups are everywhere. Any finite group has lots of P subgroups, and using a bit of class equation you can show that any finite P group, order of power of a single prime P, cannot be a simple group unless it's symmetric order P. That's because it's got central elements in it. Right? Any non-trivial finite P group has got non-trivial center. And so if you're searching for finite simple groups, you immediately look for groups whose size has at least two different primes dividing it. And you might wonder, are there any with exactly two? And the answer is no. Okay, so that's P, Q primes. Suppose I have a finite group of order P to the alpha, Q to the beta, hence the name of the theorem. And the claim is that such a group is necessarily solvable. No non-abelian finite simple groups whose order, as was shown, equivalently, this is the same as if mod G is P to the alpha, Q to the beta, and both alpha and beta are not trivial. Trivial cases when one is 0 or something, then G is not a finite simple group. It has a non-trivial proper normal subgroup. Certainly, if G is solvable, then there'll be lots of normal subgroups. Conversely, if this is true, then you can go by induction on the size of the group to prove this. Right? Take some non-trivial proper normal subgroup n, then n is still has order of this shape, and so does G mod n. And so both n and G mod n are solvable. Therefore, G, which is an extension of n by G mod n, is again solvable. So we're going to prove this. Who hasn't taken group theory in 20 term last year? Please, don't be shy, I will... 1, 2. Okay, that's enough. Sorry for the rest of you. I'm going to remind you a bit of silo theory. Okay, so this is, the proofs are not examinable, but the statements are, I think. So there was something called Silo's theorems. So let me just do a brief reminder of Silo's theorems. So let's say we have a finite group of order b to alpha m with p not dividing m, then a silo p subgroup G is a subgroup P such that the order of P is the maximal possible power of little p that can be allowed given Lagrange's theorem. Right? Lagrange's theorem tells us that the order of any subgroup is a factor of the order of the group. And you might wonder about the converse. Of course, you've seen examples in your first courses in group theory where the converse fails. A4 has no subgroups of order 6, even though 6 is a factor of 12. However, if you look for factors which are prime powers, maximal prime powers in particular, Silo's theorem tells us that they always exist. These are the theorems. Let's write sil PG, all such P's. Silo P subgroup. Okay? So first statement is that this set is non-empty. So always at least one. Second of all, GX transitively on this set by conjugation. Any two Silo P subgroups are conjugate. And furthermore, this being the case, by orbit stabilizer, you can calculate this set of the number of Silo P subgroups as the index of the stabilizer of any particular one. The stabilizer of any subgroup under conjugation is its normalizer. Right? So, but the normalizer normalizes any particular one, and therefore its index is co-prime to P. And furthermore, part C says that this index is congruent to 1 log P. I don't think I need this for Burnside. Why not? Okay, this is what divides M. Right? M is co-prime to P, remember? It's the prime P part, not G. And this number, NP, I think it was, is congruent to 1 mod P. That follows from some lemma about fixed points in the actual finite P group. And there's always at least one fixed point. Okay, good. So that's Silo's theorem. So let's try to attack Burnside. I want to show this. How do we start proving pure reduction? Right? subgroup for p without p to beta, apply Sealer's theorem to prime p, then I have at least one Sealer p subgroup big P. Right, that has order p to the alpha. Finite p groups have a non-trivial center, so take a center and it's called G. And then the lemma, this is reality, tells us that the conjugacy class in G of this center of this element is a power of Q. And this is obvious from orbit stabilizer, right? You know that the orbit in the conjugation times the stabilizer, which is the centralizer, right? But the fact that G was central is equivalent to the subgroup P centralizing G. And therefore its index is the power of Q. Whatever the centralizer is, it's bigger than P, so this will going to be a divisor of this, which is Q to the beta. And that's all that's left.
Why did the order of G become P sub alpha times Q to the base instead of P?
I'm assuming G is as in, I'm going to prove Burnside, right? Assume. So this is the first clue. You might naturally sort of think about central elements in P and find that in any such group you will have a conjugacy class with a funny shape. Its order is a power of a prime. And so the heart of the theorem is that actually there aren't any such finite simple groups with this property. Theorem 13. GBNE. Not necessarily that one. Simple group. Finite group. Suppose the size of some conjugacy class is a power of a prime. And you have to assume that this is not something stupid like I mean, you could always have a central element, then it's stupid. If you have a non-trivial prime power, then we're going to see using character theory, this is where the representation theory comes in, then G is a non-trivial proper normal subgroup. Not a finite simple group. And so I think now, if you believe this for a second, then Burnside follows. From Silo, together with this, together with the fact that P groups have a non-trivial central element. Write this out. So we have, I'm trying to show that G is not a simple group. And might as well assume alpha and beta are at least 1. So let P be a Celer P subgroup. By definition of Celer P subgroup, its size is P to the alpha. Right? So raise it back from prelims, I think. Finite P group, a non-trivial finite P group has non-trivial center. this fact? Yeah. Class equation, look at the conjugacy classes. They all have sizes order of p, and 1 has size p to be 0, so there must be at least one other class, which is not a multiple of p, and sorry, which is a power of p and not a multiple of p, which is then a singleton, and that gives us a non-trivial element. So pick something. Pick G central, non-trivial. Then we've got this theorem. Number 7.12 tells us that this is a power of q. And it can't be trivial power of q, because if it was, then this element would be central. And then we're done, right? Anyway. Got a non-trivial central element, then G is not a finite simple group. Okay, so that puts us in position to apply this. Good. So we've reduced Burnside to this. Where we're going to get a normal subgroup from. Kernels of representations. They are always normal subgroups, right? We're going to use representation theory. One of the first motivations of representation theory, I said in the first lecture, was, well, it's a group homomorphism to something manageable, so, and furthermore, by the first isomorphism theory, group homomorphism will have a normal subgroup, and the image is a group of matrices representing a group. Normal subgroup is interesting anyway. So we're going to cook up, using algebraic integers and such, a non-trivial proper normal subgroup. So let's go. Now there's going to be a lemma in the middle, I'm going to relegate the lemma to the end. Well, we have the character theory. Character tables are square and all that. And, have R irreducible representations of the group. Right, and I want to show that at least one of them is not faithful. Well, the first one is no good, right? So we have to forget about this one. Trivial character is no good. It's irreducible, but unfortunately it's very unfaithful. It kills everything. Right, so you focus on this lot. We'll go for contradiction. Why not? If the theorem fails, it better be the case that the kernels of these guys are all trivial. Why? Is that obvious? Yeah, because otherwise, if you've got a finite simple group, right, and you've got the kernel's non-trivial, and the kernel being a normal subgroup must be everything. And that would mean that the rho I is trivial, right? If the kernel of rho I is 1, right, I assume, why not? G is a finite simple group, then rho I actually cannot be non-trivial, because then this is for all I from 2 to R, else ker I is G by the finite simple group, but then actually rho I of G is the identity matrix, right? That's no good. How can you have no useful representation which squishes everything? Only the trivial representation has this property, right? Okay, and that's not possible. Okay, good. But then there's another trick we can do. This means that the non-trivial reducible characters are faithful, and so then G is isomorphic to its image by the first isomorphism theorem for all I, and this image is a finite subgroup of some matrix group, right? And this group is not a simple group, it's an infinite group which has a center. Okay? The scalar matrices are in there. So we consider rho I G intersect scalars C cross times the identity matrix, right? I and I. Well, this is central in here, so this intersection will be central in here. That's no good if we're looking for a finite simple group. So this has to be trivial for all I. Right? If it wasn't, then this would be a central subgroup, right? Of rho I G, hence trivial. Because this is a copy of G, and G is a finite simple group. Okay, so we are going to then, nevertheless, cook up for some I. Right, so it's enough to prove what there exists some I from 2 to R, and there is some J from 1 to R, such that rho I G J. Right, so this is supposed to remain. You think about the character table of the group. You've got the characters going down the rows and the conjugacy classes listed G1 up to GR. So the claim is that we're going, well, at least one of these representations sends at least one conjugacy class element, so one group element, to a scalar.
Sorry.
Yes?
I'm a little bit confused about on the previous point.
What?
So you look at all the irreducible linear representation. So why there's something like GL and I or C? Because it's linear representation. Why?
C linear.
C
Everything
linear.
C.
Yeah, but we look at linear representations, right? Just one-dimensional representations.
No. That's my jargon for linear character.
Oh, okay.
Sorry. Jargon.
All right.
Linear character means one-dimensional. All representations are linear. So,
Okay. All right.
I mean, there are also permutation representations, right?
Yeah.
In groups acting on sets, you had a group acting on a set giving you a function from group to symmetric group. Okay, is everyone happy, or this will be enough? Yeah? Because if we manage to do this, then we'll actually exhibit some central element in our faithful copy of the finite simple group G, which is no good. In the lecture notes, you will find yet another way of presenting this logic. It's a bit fiddly, but this is possibly the clearest, but yes.
So is each GJ like a representative from every conjugacy class?
Each what?
Each GJ, and is it a representative from
Yes.
every? What if like GJ is the identity?
Well, it won't work then. I didn't say which one it was. There exists some, at least one entry in the character table That's the proof. Has a funny arithmetic property which implies that the corresponding endomorphism is a scalar. That's how the proof works. The proof scans a character table, does some algebraic number theory with it, and finds at least one entry which is so big in absolute value that it forces this property. That's how the proof goes.
I mean, like we need GJ to not be the identity, because if GJ is the identity, then the identity is like naturally presented.
Are you happier?
Yeah.
Yeah, I think you're right, yes. The statement was trivial because I could take GJ to be one, is that right? All right, thank you. Right, so we have to scan the character table. And we're going to use, in the first application last lecture, we used row orthogonality, now we're going to use column orthogonality. Use column orthogonality. Theorem, what number it was? 523. So, for some G, I've screwed up. Actually, what am I proving? I'm proving comes to a G. Thank you very much, Felix. I've got a G already. It'll be this G. It's this particular G which will work. Never mind that. It's a strong mistake. Okay, we'll just look at the Gth column. So what does it say? It says that the, well, you can compare it against any other column. Which column do I want? I pair it with the identity column. What's column G? Again. Well, the first row is a trivial character, so 1 times 1 always. And I put the first column with the bar in it. Right? And G is not the identity element, otherwise its conjugacy class would have size 1. And so the inner product of, we have two different columns, therefore they're orthogonal. And that's what the relation says. So chi I is trace rho. So what do we know about this relation? We know that G has a conjugacy class which is power of Q. So something to do with powers of Q, maybe mod Q. We all know, would know that these guys are algebraic integers, right? Actually, sorry, these guys. Right, by 7.5 because they're sums of roots of unity. And these are actual integers. So let's think about Q. Q is the power of prime called Q. I should get on with it. So think about Q. Is it the, what does Q do to these things? Could it be that, could Q divide the degrees, all the irreducible degrees other than the trivial one? If these numbers are all multiples of Q, then I can take the one to the other side, divide by Q, and I get that this fraction algebraic integer. Yeah? Because these numbers are whole numbers, and this guy's an algebraic integer, they form a ring. That's no good. Right? What? Sorry. This is not an algebraic integer. Contradiction. Because the only algebraic integers which are rational numbers are whole numbers in this one. And so no, the answer is no. But we can do a bit better with that actually. In this sum, maybe some of these character values are actually 0. Right? And if they are 0, then it doesn't matter whether or not q divides this number. I'll still get the same result. So, same reasoning shows that there must exist at least one index, one irreducible representation I, and that's where it comes from, such that two things happen. This number is non-zero, otherwise it would not contribute, and q doesn't divide the corresponding degree sums. That's what you get from column method analysis. Good. This is going to come in, by the way. And now comes some funny manipulation with numbers. It's a very clever proof. Lots of ideas coming together. But we need it done. So we have to use the given, right? We also have this conjugacy class is a power of q, right? Non-trivial power of q. So that being the case, this character degree is co-prime to this conjugacy class size. This is a power of q, this is not a multiple of q. And that means I can get the Zoot's lemma going. Find integers a and b, such that a times the character degree plus b times the size of the conjugacy class is 1, and these things are going to get massaged to get something here. So what we're going to do is we're going to get rid of this number in this conclusion. Okay? Hence, you multiply this equation by chi I of g over chi of 1. By the character degree, I will get, so the first number gets replaced by the character value. The second number, I've got my A's and B's switched around. Oh no, can I manage? That's this special thing, right? The value of the conjugacy class sum here appearing. And that's chi I of g over chi I of 1. Good. So hence, the fact that algebraic integers form a ring, together with the fact that the value of the central character of irreducible representation vi, if you like, on the conjugacy class sum of g is an algebraic integer, this guy. Means that the right-hand side is an algebraic integer. We got rid of the conjugacy class. Okay? And this is no good. So, it's no good. Contradiction. And the contradiction is that this forces all the eigenvalues of rho I of G to be equal by the lemma below. So if you just assume this for a second, and that's it, right? I wanted to produce at least one irreducible character where the corresponding linear map is a scalar, right? And that's, like we know that if all the eigenvalues are equal, then it's already scalar, right? And it can't be that the identity matrix, because if it was then G, then rho I would not be the trivial representation. That's a contradiction. And that completes the proof. Modulo the lemma is the lemma. It says the following. Suppose I have n roots of unity. Take the average. You see, that's what this thing is, right? It's the average n, and it's this number, roots of unity, the eigenvalues of rho I of G. Then, if alpha is an algebraic integer, then two things happen. Either alpha is 0, that could happen, but it doesn't because I assume that I of G is not 0, right? That's okay. Or, no, the only way the average of n roots of unity can be an algebraic integer is if this average either 0 or the order. In which case, of course, this is just like some zeta. So this is not obvious. Proof is not examinable, so I could skip it, but I have to give it. And finish the proof. Proof needs Galois theory. That's the reason it's not examinable. Everyone's doing Galois theory, right? That's all right. Tiny bit of Galois theory is needed for this. To the effect that the invariance in a cyclotomic extension is the rationals. Right, so let's go. So I've got some bunch of roots of unity by taking the least common multiple of the particular orders. I can assume that they all are roots of unity of some very large order. Right? You may assume that there exists an integer k and a primitive k root of unity called omega, except I'm not allowed to write this on the board, such that the zetas are integer multiples of omega. Okay. So that being the case, at least they lie in this particular K cyclotomic extension. This is a Galois extension of Q. Cyclotomic extension to Galois, or Galois group. And we have compute it for you. Integers not K units, but that doesn't matter for this argument, doesn't matter what the Galois group is. It's validation of the Galois group. Curly G, the group of automorphisms of this field extension. Right, and so then how do you prove this lemma? This is some crazy complex number, algebraic number. We're going to force it to be rational by taking its norm. When you do algebraic number theory, you will see norms and traces as well, so this is standard. Okay. So consider norm. We're going to call A norm of alpha, and this is defined as the product of all the conjugates of alpha. So there are a number of things we can immediately observe from this. Alpha is an algebraic number being a Euclidean combination of zetas, but actually we're assuming it's an algebraic integer. And so if alpha satisfies a monic polynomial equation with integer coefficients, and I apply some automorphism of rings to it, then this image also satisfies the same equation because sigma fixes. Obviously this is, again, an algebraic integer by the fact that products of such are again such. Okay, good. On the other hand, it's obviously Galois invariant, and so by Galois theory, this is where you need Galois theory. Taking all possible Galois elements. So this is my Galois theory base. And this is Z on what I proved earlier. Right? Good. So what? It's a crazy proof. So this A, whatever it is, it's a whole number. By taking the norm of this average, we've got a whole number called A, but we knew that the absolute value of alpha is at most 1, because the absolute value of each zeta I is 1, so by the triangle inequality. However, mod alpha is less than or equal to 1 over n sum mod zeta I, which is 1. Because the absolute root of unity has absolute value 1. Now I've got an integer, alpha is an algebraic integer of absolute value 1, and therefore all of its conjugate also have this property. If you don't believe this, just apply sigma to the zetas and apply the same triangle inequality. Okay? And therefore, mod A, which is product of norms, is at most 1. It's a very small number. And therefore, A, what whole numbers are there with this inequality? 1 minus 1 is 0, right? Can't be 0, because if it was, then at least one of the sigma alphas would be 0, but then alpha would be 0, which we're assuming it is not. Good. Okay. So in any case, absolute value of A is exactly 1. And therefore, we have this equation for roots of unity, and I think we've seen this on the problem sheet. Right? You can't reach n by applying a walk of length n by adding roots of unity, right? The only way to get from here to n steps in vectors of length 1 is the horizontal line, right? It's an exercise. Sheet 3. Some question. And the conclusion is that they're all equal. And if they're all equal, then the average is also. That's what I wanted to prove. Completes the proof of fantastic. Merry Christmas.